Okay, like I said, I received an email. It seems like there is another session which I cannot find right now, this email for our class. That's fine. Okay. So I guess probably some people are using a different link or another link from last time or something like that, and that's probably there in there. Anyway, today is basically the second chapter that we're going to get going on it. We're going to do something different today. We're going to break into sessions, but I would like not to do that right away. We will basically start the content first. We're supposed to cover chapter 2 today. So, and you received the content for chapter 2 yesterday. There is no quiz yet for this one. I know that there is one for chapter 1. So you will have different assignment for this one. So it's not always that you're going to get a quiz for each chapter, so that you guys know. So that's one thing that that is going to be slightly different for this one. So let's get going a little bit with the content down the road around maybe 8:10 or something. We're going to break into groups. We're going to have each group will have its own assignment. And let me start by uploading a file in here to Zoom. So where is the sharing the file? Oh, wow. Yeah, file. Okay, let me find the file on my computer first. You guys will have the link on the chat, so you want to have that chat open. Okay, you guys should see a file on the chat that says topics 1 through 5. If you can please download that file. I know probably some of you are using phones and probably, and I know that we said that in the technology requirement, we really need to have computers. So if you are using a phone, once you break into a session, basically your peers will share with you the file and basically start working you on the file. There are 5 topics in there. Depending on how you're going to be broken down by Zoom, basically you're going to be put in a specific room. In that room, if you are in room 1, you're going to pick up page 1. If you are in room 3, you're going to pick up page 3, and so on and so forth. So if you are in room 4, the topic for you to look at in that specific file that I'm hoping by now that most of you have downloaded, you are going to look at page 4. So basically each group will work on a specific page. You're not going to be working on all of the pages in the same time. And then after you finish your group, we're going to give you between 5 to 10 minutes to basically discuss the prompt, come up with answers, and then you can come back in here after we go back basically together, and we're going to have the discussion basically answering all of the questions for all these different topics. Okay, the person who probably came late, do you guys see, does this problem only for Sarah, or does everybody else has the same problem? You don't see the file in the chat. Okay, so probably one person at least sees it. You need to go to the chat and check on it. Okay, let me try to upload it again.
I don't think those who joined later in the meeting will see it.
Yeah. Okay. Okay. Do you see it now for those who came in late? I know that there are a couple of people who joined in yet. Okay. Monica, you still don't see it? That's strange. You were here from the beginning. Yeah. Anyway, I'm going to upload it. Let me do something different in here. I'm going to upload it to Canvas just in case, but I don't want to do that because Canvas takes a little bit. Okay. When we break into sessions, you guys will be in a group, and one of you guys hopefully will have the file. If not, then I will go into that group and upload the file, because I'm going to be visiting each and every one of those groups. So you're not going to be working by yourselves. Does this sound like a good plan, at least to proceed from now on? Because some of you do have it, at least one person still does not see it. Okay? Yes? Good or no? Shall I proceed? Okay, very good. So let me share with you the file that we're supposed to start with. We'll break around 8:10 or 8:15, okay? So basically today's topic is about Newton's laws, which is a big deal in physics and physical science in general. It is really the foundation upon which a lot of the work that you do in science, especially in physical science, is based upon. So these laws are extremely important. Once you understand them, and you understand them thoroughly, you should be able to understand anything that has to do with any of the laws, the fundamental laws. There are things that these laws cannot be applied to, namely the things that move extremely fast or supermassive objects, like, for example, when we're dealing with black holes, or we're dealing with the things that are moving extremely fast. That's the realm of a different physics, different physical science, which is based on relativity. And we'll be talking about that topic toward the end. There is also another place where these laws would not be able to be applied, because they will give you wrong results, and namely for the very tiny and the very small, the atoms, to be more specific. And we'll be talking about that. That's unit number 2. That is also where these laws break down. If you are anywhere in between, namely macroscopic objects, objects of size that we can see and handle with our own eyes. Like, for example, I always have something in here handy with me, but today I lost it again. Anyway, an object like this one, if I drop it, it's going to fall per this laws, okay? This is the laws that govern that. Objects on a day-to-day experience, cars, anything that you can think of. These laws will basically help you understand them and solve them. And engineers, day in, day out, that's actually what these laws they work with, for the most part. All of our technology is based on these laws, for the most part. Now, electronics is based on quantum mechanics. That is not these laws, or I should say the microelectronics part of it, but the big aspect of it, it's still based on these laws. So these laws are extremely important. They are really very, very important. And there are only 3 of them, 3 laws, okay? And they help us understand everything around us. So there is the first law, the second law, and the third law. These laws basically can be put this way. The first law, and we're going to go in detail about this one, state the following. If an object, how many objects I'm talking about? 1, okay, is under no net forces, so we have 0 forces. 1 object, 0 forces. In this case, that object will remain at rest if it was at rest to begin with. Now, if it was moving, it's going to continue moving in a straight line with the same speed forever and ever. So that's basically what this thing is. If all you have is just 1 object, and you tally the forces and you find 0 forces, or they cancel each other, it's the same thing, it amounts to the same thing. So if the net forces are 0, or in actuality there were no forces to begin with, then that object will stay in its place forever and ever, or will keep on moving in the same line with the same speed forever and ever. One of the two. There is no other option for this object. So that's the first law of mechanics, or first law of Newton. The second law of Newton basically takes the following scenario. You have 1 object, and now you have a force applied to it. So initially there was no force. For the first law, there was no force. Now we have a force or a net force. That means there is more than 1 force, but they basically result in one of them. You add them together and they basically become just one force, okay? One is pulling one way, the other one is pulling the other way, and another one is pulling somewhere else, and so on and so forth. And you add all of their effects and you find what is called the net force. Now, you have one object, any force. Then in that case, the object velocity will change, either in magnitude or direction. And we know exactly the rate of change. That rate is equal to the force itself. And then it's impeded by the inertia of the object. In other words, you have to divide by the mass. So that's basically the second law. The second law says you have one object and net forces. The third law now, and that is really where the power of this laws come in, is when you have more than one object. Because the universe is not made up with a single object. So if we're trying to say that these laws are universal and explain everything in the universe, and we explore the first law that says that one object, no forces, the second law, one object, one force, well, how about if we have more than an object? Well, that's when the third law comes in. The third law says that if you have more than an object, now there are two situations in here. If there is these two objects or more, interact or do not interact. That's the only possibility for them. If they do not interact, we treat each and every one of them by themselves. Then they either fall under the first law or the second law. Each and every one of them could be under no net forces, or each and every one of them could be under net forces, or a combination of both. Some of them will be under some net forces, others will not be under some net forces. Some of them apply the first law, some of them apply the second law, and I'm done. But there is a classification of those objects where they actually do interact. So if they do interact, now I need to know how am I going to deal with that? The third law tells you if they do interact, and we're going to talk about forces and interactions, then in this case, if one of them exerts a force on the other exerts a force that is equal and opposite in magnitude. That way you have done everything. You know everything about the system. You know if objects, they are not interacting, then you treat them with the first law or the second law. And you know them if they interact, then you treat them with the third law. And you have basically described every single situation that you can come up with. That's why they are powerful. That's why these three laws, they're the most important thing in terms of what we do in a day-to-day affair, because as engineers or as technicians or scientists, give me any situation. It doesn't matter how complicated it is. If I can't tally the forces, that's really what the caveat is. If I know the forces, then I'm done. Then I just solve these things. I mean, if I can't solve it, just put the thing on a computer and that's it, and have the thing give me the answers. That's the power of these three laws. That's why they're the foundation of all of physical sciences, basically, whether in your chemistry, whether in geology, whether in astronomy. The only exceptions, as I said in the beginning, is the objects that move super fast, almost the speed of light. These laws will not help you. You have to invoke relativity in that case. Near supermassive objects, for example, the sun, Mercury, for example, is very close from the sun. These laws probably will not work 100% for it, and we know that. So there are exceptions to these laws that we can basically, we have to invoke higher order laws, new laws basically. And the objects that are super tiny, for example, an electron going around a nucleus and the hydrogen atom, for example, we cannot use these three laws. They are not going to work. Because for one thing, for example, the electron has a negative charge and the proton has a positive charge, and all what's happening in this case is the electron should smash into the proton. But you say, okay, it's moving super fast, just like the planets do go around the sun super fast, so it's going to maintain its orbit. Well, there is another problem with that, and that is the electron should radiate energy, and it starts losing energy, and ultimately is going to fall, also collapse on it with these laws. So these laws will not work then. You need new physics, and that's basically the limits of these laws. Other than that, they are so powerful. They describe everything we do on a day-to-day basis. So this is, in a nutshell, the last few pages. I mean, the summary of the Newton's three laws. So right now, I think we have, I'm going to stop, we're on slide 2. We're going to stop in here, and we're going to break, like I said, in 2 rooms. I'm going to upload just one more time. I know there are a few people who came in late. That file for the few people who just came in. You need to open the chat on the bottom. It says chat. You need to open that, and I'm going to upload again the same file basically. If you have it already, ignore this file. If you don't have it, it should have been uploaded again. It's 353 kilobytes, so I try to make sure that it's small enough. Okay. Monica, do you still have? Okay, very good. Okay, so I'm going to break the entire group basically in about 5 groups. Okay. So you should have about 3 people in your group. Okay. And again, Canvas. Oh man. Okay, Monica, I will see which group you are in and see there, and hopefully somebody else will have it. Okay. Anyway, you're going to be in a room, and depending on that room, you're going to pick the page. Okay, so if it says you're in room 1, you're going to pick a specific the page 1. If you are in room 5, you're going to pick up page 5. You're not supposed to go through the entire document and work on it for the entire group. You'll only have a specific task, okay? So it's 8:17. We should finish this roughly between 8:22 and 8:27, okay?
And then what do we do after we've looked over that page?
After you do, you answer the question, and we meet together and we discuss the answers, all 5 pages together, correct? Yes?
Got it. Thank you.
Yeah, okay. You need to accept to join. Hi, Sarah and Masada. We were in actually breakout rooms. I don't know what happened to you. Probably you joined us late or something. So let me send. Yeah, let me send you to.
Then I exited out. I'm like, oh God.
Yeah. Okay. Okay. Let me see if I can put in room.
Hi, Professor. So, can you hear me?
Yes. Yes, I'm here.
Okay, cool. So I downloaded it, but then when all the three of us girls went to our breakout room, none of us could find it in our downloads.
Oh. Okay.
And
So,
it actually, when I did save it to my computer, gave me a green check mark, but it wouldn't open. I couldn't find it.
okay. Probably it saved it in a folder that is maybe not typical where you're going to.
Well, I changed it though. I specifically changed it to documents and I changed the name of it. So.
Okay. Maybe your computer
Mine, I
started.
didn't have it.
Yeah. Okay, so it's 8:26. Maybe you're going to end all the breakout rooms and we come together. And basically, they will join us again and we'll talk about these files together and try to answer the topics. Okay?
All right, thank you.
Okay.
Maybe we could go over page 3 while we're waiting.
We're going to go through all the pages. Everybody is coming back in here. Okay. Yeah, we still have a few people from room 4.
Maybe like next time we could have it sent to us earlier, like through
Yes,
Canvas.
yes. Yeah, the thing with Canvas is that this file is, because it's all images, I tried to send it earlier and it was telling me it does not meet the something accessibility or something like that. Okay.
Gotcha.
That's probably why the link wasn't working for some people, for the memory and stuff.
I see. Okay, so probably we'll have better files next time, or written in text instead of having them into like PDF or something like that.
Or even through email.
Yeah. Okay. Hi, everybody. You're back in here?
Yes.
Okay, very good. Okay, let me see if I can find the file on my computer now and share it with you so that we can have a discussion about each and every one of those topics. Okay, where is the file on my computer? Okay, never mind. Let me see if I can open it from the chat session myself. Oh. Okay, here is the file. Let me open it. And let me come back again to Zoom and share screen. Okay, this is group 1 basically, and topic 1. Which of the statements below is a scientific claim? And group 1, you guys can either chat or can basically tell me which one do you think is not a scientific claim. Human beings will never set foot on the moon. Some of the laws that govern nature cannot be detected by scientists. It is quite possible that in some other galaxies, the laws are fundamentally different than the laws we are acquainted with in this galaxy. Somebody thinks it's claim number 3. Can we test this for failure? Can we say that it is possible that in some other galaxy, the laws are fundamentally different than the laws we are acquainted with in this universe? Of course, we cannot test this, okay? So that's really something that, yeah, you're right. I think this is correct, okay? Okay, group number 2, they had the assignment, the great philosopher and mathematician Russell wrote about ideas in the early part of his life that he rejected in the later part of his life. Do you see this as a sign of weakness or strength? What do you guys think? Strength. Yes, it is. That's part of the scientific attitude. Basically, yes, you believe in something, but if you're confronted with evidence, you should be ready to accept basically that you were wrong. And this is actually strength. This is not weakness. So you guys are right on this. Okay, and in here it says, note, this is for group 3, note the readings on the scale. Burl, the painter, has a weight of 600 Newton. So he's got 600 Newton pushing down and carries a 100 Newton bucket. So there is 100 Newton plus 600. That's 700. And carries 100 Newton. What is the weight of the scaffold? What did you guys find? Remember, there are 2 ropes pulling on it by one 700 and one 500 for a total of what, 1200 up, and he's pushing with 600 Newton. In addition, there is another 100 Newton. So how much is the weight of the scaffold need to be? 500. That's correct, because everything has to add up to 0. His 600 and the 100 of the bucket combine to cancel one of the 700s. So we need to cancel the other 500, and for that, this must be 500, okay? Otherwise, this thing starts to move upward, okay? Page 3. You have basically a gun that shoots a bullet, and the bullet goes in this spirally path that is forced around it. But the minute it's free, is it going to go through path A, B, or C? By the way, this is not an easy question, okay? A lot of people get it wrong. Even people who take physics, I mean, and other courses. So which one do you think? Path B? Do you guys agree? Yes, because at that point it's free from all forces, and again, then there is no net forces. So if it has a speed, it's going to go in straight line forever and ever. Okay, we're neglecting gravity in this case and all of the other forces. Okay, so that's correct. Path B. Okay, and this is the last topic, and this is similar in a sense to the previous one. When the ball at the end of the string swings to its lowest point, the string is cut by a sharp razor. So now which path is it going to be? Is it going to snap and then fall straight down, free fall? Or is it going to go on path that is described by B? Or is it going to go in some sort of a... Some people, they get this wrong too, and it seems like you guys are on top of it. So it goes like a projectile, basically. It's going to fall. Like when you throw a rock, it's going to fall. So this is correct too. Okay, good job, everybody. Okay, so next time, I think we're probably going to share this stuff ahead of time and make sure that we have the topics ready. And when we break into sessions, everybody knows exactly what is basically we need to do so that we work together and come up with a consensus. But I'm proud of everybody because it seems like everything you did, you got it correct in here. Okay, we may not finish the lecture today, and that's fine. You guys can probably finish it because we did most of the lecture, honestly, when we did this slide. We talked about all of the 3 laws. Does anybody have any question about this activity or anything like we just said?
No.
Okay, very good. So, so again, this is the law of inertia. Basically, this is a typical example that you see magicians perform, and it's really no magic, no nothing on it, so it's very simple. You put you pull the sheet underneath very fast. In this case, because of the inertia, the objects stay in their places, and that's because they resist by nature. That's what inertia is. It resists by nature the change in motion. Okay, remember the experiments of Mr. Galileo for the incline? That's exactly what he did. He showed that. Oh. So why is this? There was an issue, Sarah's session for some reason. Okay. Sorry, Sarah, I don't know what happened, okay? Sarah Solis. Okay. Anyway, so that's the, that's just a demonstration of the law of inertia, basically, or the first law of okay, the first law of Newton, okay? And here is a question for you guys. It says that a sheet of paper can quickly be withdrawn from underneath a soft drink, can without the can toppling, because again, its gravity pulls harder on the no, that's not the case. The can has weight. No, the can has inertia. This is the property of inertia. Okay, objects tend to resist the change in their motion. Okay, so you really, yeah. Okay, when you pull hard on it, when you pull super fast on it, in that case, you didn't give enough time for the can basically to change its motion. So in this case, it's resisting the change in motion. So the correct answer should be C, isn't it? Okay. So if you swing a stone overhead in a horizontal circle and the strings break, the tendency of the stone is to follow
a straight line path.
Do we have horizontal on the break? Yeah, okay. Because now we're neglecting all external forces, okay?
Mm-hmm.
Otherwise, if we have other forces, then the problem can get a little bit complicated. It's just similar to activity of group B, I think. Or group, group B. Group 4 or group 5, one of the two, okay? Because again, we're going back into the first law. There is no net forces on it. If that's the case, then it's going to go in a straight line forever and ever and ever. So all of these demonstrations are examples of the law of inertia. In this case, in this example, it may be a little bit confusing. What's going on in there is that if you pull slowly on it, then you're giving a chance for the weight in here, in addition to the applied force coming from your hand onto the string, to build tension. There is clearly more force on this side, on the upper side of the string, than the lower one, because the lower one is just subject to your hand only pulling on it. The upper portion of the string is subject to your hand through the string and also through the weight of this mass. So the combination of these two external forces, basically the pull of the earth on this mass and your pull, are greater on the upper string than on the lower string, hence this will snap first. But if you come and you try to pull it, yank it very fast, in this case, the weight in here would resist the change in motion. So there is this one will snap first before the one in the upper. Try this experiment, try to do it at home, if you have access to some of the strings and things like that. And you will see at some point, if you're pulling slowly, then the upper one will break first. If you yank it, then the lower one will go first, okay? Make sure that you have a string that actually breaks, because if you have a strong string, then it's not gonna work, okay? Here again, a demonstration of the law of both laws, actually, the first law and the second law, because for you, who is basically free, in this case, the inertia will keep you on going. Whereas for the car, it's actually subject to external forces, in this case, the braking. Okay, coming from the interaction of the tires and the ground. So that's basically the second law at work. The first law is as far as you're concerned, and that's why it's a good idea to wear seat belts to keep you in a car, just in case if the car suddenly stops or something like that. And the same thing applies actually if the car takes off immediately. You will feel that your body doesn't want to follow the car, it wants to stay where it was. So that's why you're basically pulled toward the back when you accelerate the car, okay? You're going to be pushed toward the edge, to the back of the car. That's again the inertia. If you make a sudden stop, you will find yourself moving forward. Again, the inertia, your body trying to do that. Now, if you're going on a curve, even with a cruise control, even with the same speed, basically, in this case, you're not accelerating, you're not decelerating, you're not gaining speed, you're not losing speed. But if you're going on a curve, you have tendency to basically, your body starts to, if you're going to this side, your body wants to continue where it was going. So you go this way. Now, if you're going this way, because your car is trying to move this way, again, your body wants to continue in that path. And you have to have the door basically to retain you in the car. And that applies another force to keep you in there, okay? So that's an example of changing velocity, not changing speed, meaning changing direction of the force only. So the force can change, I mean, the change in motion can occur in two ways, or three ways, I should say. change in magnitude of the velocity or change the direction of the velocity or both. Okay, you could have a situation where both the direction and magnitude are changing at the same time, and that's still the second law. So this is an example again of the inertia. If the plane is moving at constant speed, you can basically throw an object in the air, and the object will follow exactly as if you're sitting on the earth. Okay, again in this case, as a matter of fact, for an observer looking at it from outside, it looks like there is a projectile, there is a motion going around, but that for you it's different. You put your cup next to you whether you're sitting in a car or sitting on the plane, and you will, if the plane is on cruise control and there are no air basically bumps or anything like that, the water surface should really be smooth and you can sip your cup as much as you want. Same thing with a car. If there are no bumps on the road and you're not accelerating, bumps meaning change in direction up and down, and that is change in velocity. So that's still accounts for, that's why you see the water or the coffee basically going up and down, because then it's not first law anymore. Okay. Here is an argument that was made initially when Copernicus basically came up with his wonderful basically idea based on a lot of observations that, look, the Earth is not the center of the solar system, but the sun is, and the Earth is moving super fast around the sun. By that time, people knew the distance from the Earth to the sun. If we are going on a circle around the sun, we must be moving tremendously fast. We must be moving about 30 kilometers per second. That means it's a lot. I mean, it's in 1 hour, it's how many seconds that is? 1 hour is 60 minutes times 60 seconds, because every minute has 60 seconds. So you have 3,600 seconds in 1 hour. I know we're not in here for 1 hour, we're less, but remember to multiply that by 30. That's 30 kilometers per second. That's how fast it's moving. So the argument against that was that, look, if the bird wants to catch the worm while it's sitting on the tree, yes, the tree is still yanked. I mean, it's still anchored on the ground, so there is no problem with it. So he's moving with the Earth, and everything is moving with the Earth as it's moving around the sun. Now, when the Earth tries to fly to catch the bird, at that point, by then, the tree and the worm and the entire Earth would leave it behind. So that was the argument against, basically, against Copernicus, saying that the Earth should not be moving. If it were moving, no bird can catch its worm. And that was the problem that actually Copernicus didn't know how to explain. I mean, he was also fearing for his own life, because he knows that the belief at that time, especially influenced by the church, was very strong that the Earth is the center of the universe and we are basically it. And he didn't want to go against that, but also he needed to come up with a rationale for this idea. People were arguing against that based on this example. Well, with the law of inertia, that's easy. That's fine. We can explain that, because Mr. Galileo came after him, and he's the one who actually laid the foundation for everything we're doing, including the law of inertia. Basically, in that case, there is no problem. The bird was already moving with 30 kilometers per second. So if it flies down, it's going to maintain that 30 kilometers per second while it's catching its worm. Yes, the worm and the tree and everybody else is moving with 30 kilometers per second sideways, going to around the sun, and so is the bird too. So that motion is not a problem as far as he's concerned. He can stay in the air, and he's not going to be left behind as the planet leaves it. So actually, not only him, but also the air also around, everything around it is moving, and there is no exception to him just because he's basically in the air. Furthermore, and that's another thing to add to this thing in here, he is actually anchored to the Earth too, even if he's in the air, because of the law of gravity, because of the fact that there is actually a pull between him and the Earth. So he's pulling on the Earth is actually pulling him and dragging him with it, even if he is in the air, even if you are on the moon. When the astronauts, for example, jump up and down, there is no air to drag them with the moon. Well, in this case, there is actually the moon itself that is pulling on them. So they are not completely free once they jump up and down. Okay. So that's the same idea holds true actually if you jump up and down in your room. I mean, the earth and the walls and everything should not come rushing to you and basically smash you on the face. And because everything is moving, so you can still jump up and down and you're fine, okay? The earth will not leave you behind it. No one can be left behind, okay? Put it in terms of one of the president's words. Anyway, so that's the law of inertia. The second law, like I said before, now we're talking about an object and their net forces. In this case, the object will accelerate. So the word accelerate in this case means change velocity. And change velocity, velocity being a magnitude and direction, change either magnitude or direction or the combination of both. Okay, one of the two. I mean, one of the three actually could happen. Okay, so in this case, if I apply force, the object will accelerate. If I apply double the force, the object will double its acceleration. That's what experiment has shown us. So based on day in, day out observations, this is what we know. You double the force, the result is twice the acceleration. This is a law that can never be broken. It's not like the man-made laws. For example, if you see the speed limit 65 miles per hour on the freeway, you can break it. I mean, I did break it too myself. I mean, I sometimes just to test the law to see if it's a really physical law or not, I can go 66, 67 miles per hour. Of course, I do it briefly, okay? So please don't do that, okay? Because you might end up, usually Murphy's law will apply too, which is another law. When you try to break the law, that's when the police officer will be in there waiting for you. So don't do it, okay? But the point being in here is this is a physical law. It can never be broken. Unlike the other laws, the man-made laws, and that's why we have officers to enforce them. This law does not need a police officer to enforce it. You double the force, there is no question about it. The acceleration will double, as long as you're dealing with the same mass. Now, if the object breaks into two parts, then each part may accelerate differently depending on how much amount of force is applied to them. That is because the inertia also plays a role in when it comes to acceleration in here, okay? So this is the law in its beauty. This is the law. This is not just a law. This is the law in physics. F equals to m times a. If there is anything you will learn from this class at all, if anybody asks you down the road, what did you learn from Physical Science 1 coming from Norco College? You'll tell them, I learned F equals to ma. The force is equal to the mass times the acceleration. If you know this one, you know a lot about physical science. This is really it. It cannot get any more, and this is it's true for an introductory course as much as an advanced course. Doesn't matter how much math you need. It doesn't matter how much math you have. If you have a full understanding of this one, you really have everything. I mean, let's put it this way. Yes, there are three laws for Newton. The first law is critical and usually deals with things that don't move, like this building, for example. It's static. Net forces are equal to 0. Architects, they revolve around the first law. They thrive on the first law because they want to build buildings that stay in place. You don't want a building under the next, basically, breeze of air or something like that, they collapse. No, you want something rigid and structured. But you want it also to be safe, and you want it also to be economic. Basically, you don't want to waste in building it. So that's what they do day in, day out. So they deal with the first law. The second law is really the one that deals with dynamics when things are moving. Anything that is not stationary is this law. Even the people who deal with the first law, they invoke the second law. They work all of the forces and they make sure that everything cancels. So if you have a building, it's supposed to sustain a certain number of people, for example, on it, you would want to have enough strength in it to maintain those. So you say, how would I know that? Okay, let's bring all the forces and make sure F equals to ma is 0. So they come back to this law. It is really the centerpiece of the entire thing that we do in physics. It is the central point. It is, like I said, not a law. It is the law. It is the main focus that we do in. And the actual wording for it is the one that you see before your eyes. There is a cause and effect in this relationship. The cause is net forces. The effect is acceleration. So if you see an object changing its velocity, meaning gaining more and more speed, or losing more and more speed, or going around in a curve, or doing both, okay, in that case, you know for sure that there must be a net force on this object. So there must be a cause to that. So this is a cause and effect relationship. The problem with this is the mass in the denominator. The more mass, the less effect of the force on the object. That's why you see those relationship. And they're trying to be visual also. Small net force, large mass, small acceleration. That's basically in a nutshell. Large net force, small mass, in this case, large acceleration. We can talk forever and ever on this idea because there's all kinds of basically subtleties in it that really brings a lot of things that we do. Okay, so let's move on and we'll come back to this idea down the road, okay? Consider a cart pushed along a track with a certain force. If the force remains the same while the mass of the cart decreases to half the acceleration of the cart, if the mass decreases, somebody pulls stuff from the cart, then in this case, is the acceleration going to stay the same or is going to be more? Because there is less inertia, less resistance. What the word inertia means, and probably you hear that word a lot, is the resistance to the change in motion. So go back in here. I know I see some feeds in here. Yes, you're correct. So it should increase. It should double actually, because if the denominator somehow goes down, let's say for example you have $10 and you want to split it on 2 children. Each one of them ends up with $2. I'm sorry, 2 children. Each one of them ends up with $5. I'm sorry. So you have $10. You split between 2 children. That each one of them ends up with $5. But if only one child, then they split it $10 on one, so that person will end up with twice as much, because the division in here increases. The result increases with basically the decrease of the denominator. So your guys are right. So it doubles. So if the cart has maybe, for example, 50 pounds and you're pushing it, and then all of a sudden you remove the big bag of 25 pounds, whatever, flours or something, or rice or something, then hey, now you are easier to push this thing. Okay? So you're right, it doubles. So push a cart along a track so twice as much net force acts upon it. So you're pushing it and you couldn't push it, you're trying to push it, and then you ask for help and somebody comes and helps you. Now all of a sudden, instead of having 100 newtons, you have 200 newtons pushing on that cart. And in this case, but the acceleration remains the same. Hey, somebody else comes in and push, and all of a sudden, it stays the same. So in this case, that means he brought his stuff too, and he put it on the cart, okay? So it's the same thing. So basically, you join the 2 carts, now all of a sudden, you have your cart, and somebody else comes in and ties the 2 carts, and now we're pushing them together. So in this case, you're right. So the acceleration should, in order for it to remain the same, the mass has to also double, because again, it's a ratio, okay? So if you double the force and the acceleration stays the same, you need to double the mass too to keep it the same. So the correct answer is A, you're right. So when an acceleration is G, this is the free fall, okay? An object is in free fall if its acceleration is G, 9.8 meter per second, or roughly 10 meter per second. This is not a typo. When you see in the bottom in here, it's 10 meter per second. That's really how it's supposed to be. It's 10 meter per second. Sometimes you will see, what is my tools in here? Comments. If I can get some of these things in here. Some people, they use the symbol meter per second squared. That is the same thing. That stands for 10 meter per second per second. So if you're reading the book and it reaches a point that it says the acceleration is 10 meter per second squared, it is the same thing as 10 meter per second per second. Okay. At one instant, an object is in free fall, has a speed of 40 meters per second. Its speed 1 second later, remember, it's gaining 10 meters per second for every second. So 1 second later, it's going to get another 10 meters per second. So the correct answer should be, yes, you're right, Sarah. It should be 50 meters per second. Because right now it's moving 40. So in 1 second later, add to it 10. Okay. So when acceleration is g, free fall, twice the force on twice the mass, the same acceleration. So basically both of them will fall with the same acceleration. Again, the number 2 cancels from numerator and over denominator. If the force is, for example, 100 newtons and the mass is 10 kilogram, 100 divided by 10, it should stay 10. 200 divided by 20, it should say 10. So that's basically a simple algebra. A 5 kilogram iron ball and a 10 kilogram iron ball are dropped from the rest. For negligible, and this is the key word in here, for negligible air resistance, had the resistance been there, this is not true. The acceleration of the heavier ball will be, yes, B, okay? A 5 kilogram iron ball and a 10 kilogram iron ball are dropped from rest when the free falling 5 kilogram iron ball reaches the speed of 10 meters per second. The free falling 10 kilogram will be the same, okay? Because the same acceleration. They're dropped from rest. They did not have a speed to begin with to add to what they already have. So it had 0 speed. That's what rest means. So when you drop them, they should gain another 10 meters per second, both of them. Okay? Now here is an analogy. The reason why the rock has the same acceleration as the feather. I mean, if you do this experiment outside of your window today, take a small rock, it doesn't have to be too big, and a feather, you will see the rock reaches the ground first, before the feather. It's because of the air resistance. This F now, the weight of the feather, is being canceled a little bit by the air resistance. And same thing applies in here too. But this is a big mass, so the air resistance is weaker, relatively speaking, compared to this one. So this one will affect it more if you do this experiment at home. Hence, it appears to be not accelerating as much and will reach the ground later. So if you do this experiment, it will fail on you at home because you don't have vacuum. But if you conduct this experiment in vacuum, it should work the same. They both will fall the ground at the same time. This analogy is similar to the ratio of the circumference over the diameter. This fact was known from the early Greeks and the Egyptians and before them, modern day Iraq, what is that area called? Babylonians, basically, they had this ratio of C over D because they were dealing with inheritance of lands and things like that. And they needed to find a way of doing geometry. So they know the ratio. And pi, by the way, is not any magical thing. It's just a number. I mean, it's just something that we basically, it's roughly 3.14. It's a number that does not have an end toward the end. So it's 3.14 something, 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 and all the way extending forever and ever. But the point being, it's a number, okay? It's not something magical about it, okay? Just the ratio of those two quantities. Same thing in here. G is just a number, the ratio of force over mass, except this one is really a number, doesn't have units. This one is an acceleration. G is an acceleration. So when we read it 10, it's actually 10. Oops. Sometimes my screen does that, okay? Thinks I'm, so when you read the 10, it's meter per second for every second. So that's the unit for G. Pi has no number, it has no unit, it's just a number. Okay, this is the experiment. When an air-filled glass tube containing a coin and a feather is inverted, the coin falls quickly to the ground, and that is because of the fact that you're dealing with air resistance in this case, because it's air filled. Okay, so they don't fall to the ground at the same time. But if it has no air, they should fall with the same speed at the same time in the bottom. When the air is removed by vacuum, the correct answer should be in here, both the coin and the feather drop together side by side, okay? So now when you have air resistance, and this is, then in this case, the object will not be in free fall. They will not have the same basically acceleration when falling to the ground. So one of them will fall faster than the other one if it has less, basically, depending on the air resistance, basically. That's what that means, okay? There is for building a parachute, basically, in this case, you have to account for the area. If it has a small area, then in this case, you're very close from free fall, and you're going to reach the ground with the big, basically, speed. Versus if you have a parachute that is a bigger area, and also what matters is the condition of the air, because if you do this experiment, for example, on Mars, Mars has less air than the Earth, so you need to account for that. So the air resistance there is different than the Earth, so that you have to account for that. And also it depends on the speed. That's what the air resistance is. So when you drop the object initially, it has no speed. So there is no air resistance whatsoever. There is no change in speed. So as long as you start gaining more and more speed, in this case, you're going to have more and more air resistance with it. If your car, for example, if your car is not moving and you put your hand outside of the window, you're not going to feel hardly any air touching your window. But if the car starts to speed more and more, your hands start to bend more and more, because the air now, there is more air rushing to your hand than if the car is standing still. So you can do the experiment in the car, but try not to put your hand all the way outside, because especially if there is incoming traffic. Okay. When a 20 Newton falling object encounters 5 Newton air resistance, its acceleration in this case should be less than g. Because remember, what the basic idea here is that it's the force. In this case, had it been only its weight, it's going to be 20. And divided by the g in this case, which is 10, it should really gain 2 meters per second. What is it? I'm sorry, divided by g. Sorry. So it's going to be 10 no matter what if there is in free fall. Okay, so it must have had 2 kilograms to do that. But if now the same 2 kilogram is subject to also an air resistance of 5, then in this case the actual answer should be 20 minus 5, which is 15 divided by 2. So its acceleration should be less. It should be 7.5 meters per second. So it should accelerate less. Okay, you guys see that? That's why it's less. Had it not had any air resistance, its mass must have been 2 kilograms to give you the 20 newtons. Okay, but now with air resistance of 5 newtons, then it's going to accelerate less, and we know exactly how much it's going to accelerate. It's going to accelerate 7.5 meters per second, and 7.5 is less than 10 meters per second. So it's going to be less than g. Okay, I have the algebra in here. When acceleration is less than g, non-free fall. As falling object gains speed, we still have about, how much, 20 minutes left? Okay. As falling objects gain speed, force exerted by surrounding air increases. Okay. Force of air resistance may continue to increase until it equals the weight of the object. At this point, no net force is applied, and the object will reach terminal velocity. This is basically what you do if you're trying to drop an object, for example, from the sky, whether with from a helicopter, for example, trying to rescue people who are flooded or something, or trying to, for example, do something, for example, drop, like, for example, the lander of Mars. There are 3 missions going on right now on Mars. Hopefully by February 18th, you guys, it's going to be a Thursday. one of them, at least the US mission, is going to have a lander on Mars. So we're going to observe that and see how it's going to land. But again, you're going to drop an object in this case from the sky. It's going to go through the air resistance. Initially, the air resistance is less, but it's going to increase with more and more speed until at some point, the object is going to fall under its own weight, and there is the buildup of this air resistance. The two forces will cancel at that point. We go back into law number 1. So yes, we used law number 2 to arrive to this answer. That was the second law. But if this number keeps on increasing on me, keeps on rising more and more and more, until at some point 20 minus 20 will be 0. So at that point, there is no acceleration. At that point, there is no increase in speed. That is your terminal velocity. At that point, you have reached your terminal velocity. You cannot gain more speed after that. That's it. That's the speed with which you're going to fall. So you guys understand the scenario in here? So that is, you're gaining more and more speed, because as long as there's still acceleration, albeit it's smaller acceleration, it's still, you're going to gain speed. You're not going to gain as much as you did in the beginning, which was 10 meters per second for every second. In this case, you're going to gain 7.5 meters for every second, for every other second. Okay, 10 meters per second for each second. And you're going to gain less and less as long as this number keeps on increasing. Okay? But you're still gaining speed. So speed is increasing, actually. Whatever it was before is going to be more now. Up to a certain point where this number becomes exactly equal to this one. Okay? At that point, the resistance, the air resistance, has no way of increasing further. And in this case, the object basically starts to continue falling with constant speed. Okay? There is no gain in speed. That is what we call the terminal velocity. Okay? So that's how objects fall. Even if you don't have a parachute, actually, and if you have high enough, you're going to reach it, because your body itself can serve as an area, and you're going to basically get enough airspeed so that you reach terminal velocity. Unfortunately, objects that are dropped from smaller heights, they will never reach the terminal speed, because they're going to gain more and more, and probably there is not enough air resistance to account for that drop in acceleration anyway. So if a 50 Newton person is to fall at terminal speed, the air resistance needs to be exactly 50 Newtons. So when we're talking about terminal speeds, you have to have the same force to cancel it, okay? So as a skydiver falls faster and faster through the air resistance, at that point, you're still faster and faster. So that means the speed, the air resistance is increasing, because it increases with speed. So the air resistance should be increasing. And now, as a skydiver continues to fall faster and faster through the air, the net force should decrease in this case, because as the buildup of the air resistance and the gravity is pulling, but there is gravity now is pulling down, but there is a bigger force on the opposite direction now mounting for it. So there is less force on it, hence less acceleration. And then as the skydiver continues to fall faster and faster through the air, her acceleration now should also decrease, because there is less net forces. Net force and acceleration, they go hand in hand. Okay? So consider a heavy and light person with the same parachute jumping together from the same altitude. So one of them has more weight than the other. One of them is being dragged bigger than the other one by the force of gravity. They have the same parachute. Both of them have the same brand, the same size, the same properties. So in this case, who will reach the ground first? Well, the heavy person needs more air resistance to account for his weight versus the light person. So in this case, he continues to gain more and more speed before he reaches his terminal velocity. So once he reaches his terminal velocity, at that point, he will continue with that constant speed. So he's going to have a higher velocity, therefore he should reach the ground first. This one will reach his terminal velocity very quickly, which should be less than this terminal velocity, and hence he will have more time before he reaches the ground. So the heavy person should reach the ground first because of the fact that he got more mass, and more mass means more weight, which means that there is more time needed for the air resistance to cancel that weight, gaining more and more speed. So his speed will be higher and speed accounts to time. I mean, if both of them were dropped from the same height, then because this one is moving faster, will reach the ground further and faster than this one does. So the heavy person will reach the ground first. So again, we talked about this one in the intro, namely that there are forces. Forces, you can think of them. You're really not all of them as such. It's simply a push or a pull. You don't have to have a contact for that either. For example, the Earth pulls on object even if it doesn't touch them. This object, if I let go of it now, it's going to be pulled toward the Earth. There is no contact, at least. Right now, I'm the one who's holding it, okay? Yes, I am on the ground, but that's an indirect contact, if you like to call that contact. Once I let go of it, the object is still being subject to the pull of the Earth. So that's really what you need to know. So there could be contact or contactless force, in this case, push or pull. If I have two magnets, for example, and put them next to one another with the same side, then they will repel each other. Again, that's push. Push. If I flip them around, they will pull toward each other. So that's basically the idea behind it. Excuse me. Interaction, on the other hand, happen between two objects. They exchange, basically, they swap information. This is how I'm going to push, this is how much, so on and so forth. So in this case, in the picture, the girl is pushing on the wall is pushing back on it. So in this case, there is a force, that is, if she pulls her hands, in this case, there is no interaction between the girl and the wall, okay? So the third law, really, whenever one object, and there is this condition, it has to happen first. When object exerts a force on a second object, so this has to be met first. The second object exerts a force on the equal and opposite to the force on the first one. You've probably heard of it under different names, this law, action, reaction, principle, whatever you want to call it, okay? So it's the third law of Newton. So we covered all three laws of Newton. That's it. That's all you really need to know in terms of physical science. You know these three things, you're in great shape, okay? So action and reaction forces, one force is called the action, the other one is called reaction. This sounds like, if you have seen that movie, it was in the early 2000s, what is it? It's based on the book by The Cat in the Hat, Thing 1 and Thing 2. And they look alike, so they call them Thing 1 and Thing 2. The same thing applies in here, okay? This is action, reaction, which one you call action, which one you call reaction. It doesn't matter. So the fact that I called the girl acting, it's really just during the interaction, you can't tell which one is which, okay? Yes, I know the girl approached the wall, but that's just before. But the minute the interaction happens, you cannot really distinguish between action and reaction in this case, okay? Are co-pairs of a single interaction. They adjust interpretation of that interaction. Neither force exists without the other. So just to argue that the action is more valued than the reaction, and this one, no, the action itself cannot really exist without the reaction. Are equal in strength and opposite and always act on different objects. So you have to have two objects. You cannot have a single object doing that on itself, okay? So a soccer player kicks a ball with 1500 Newton. So how much is the reaction of the ball? It should be the same. Okay, that's the third law at work. So examples of the third law. Third law is really what makes a lot of things happen for us too. Yes, we have a car, and if you put a car on an icy day, I know we don't have ice in here, at least unless you go to the mountains. The car will not go anywhere. If you put, it's going to basically spin in its place. Same thing for you. If you try to move, you cannot go anywhere. And that is because friction is really required for motion to happen. So because the tires press on the ground pushes the car forward because of friction. So what if you are ever asked what makes the car move, it's actually the ground that does move it. It's the force of friction from the ground. I mean, the internal forces, the combustion and all of that, and the gas and the the pistons going up and down and all of these things. And they're just internal forces. They cancel each other mutually until that motion basically is translated into a rotational motion in the tires. Now the tires participate in the whole process, the internal process of the car, and they want to spin also because everything internally is acting under action and reaction. The minute the tires try to spin, at that point they're interacting with the external universe, namely through the asphalt. At that point, the asphalt will apply a force to push them forward. Okay, so that's basically. So the tire is trying to spin, going backward. The ground will push it forward. Same thing for a rocket. The rocket pushes the air. Pushes the exhaust from the engine. The exhaust will push the rocket forward. That's how you have rockets. The rockets, they don't have ground to basically accelerate on or anything like that. So basically, that's why you see the smoke coming out and all of the exhaust coming off of it, because you would want to gain speed. Now, if you happen to be in interstellar space or even space and there is no air or anything like that, so you can't push against anything. You can swim by yourself and you're going to go anywhere. But if you have a gun, and that's what you do, you shoot it in one direction and you end up in the opposite direction, just as Matt Damon did toward the end when he tried to save himself. So that's something that to get himself to where his saviors were coming to pull him. So again, this is another example. If you drop an object, as much as you think that the Earth is pulling on this object and bringing it down, this object, no matter how small it is actually pulling on the Earth with the same force. Okay, with the same amount of force on it too. When you step off of a curb, Earth pulls you downward. The reaction to this force is the same. It should be you also pull the Earth upward. Okay? Action, reaction, different masses. Now, for example, for the example of this example on the Earth, you have to be very careful in here. Why this object looks like it's moving and I don't see the Earth coming and rushing up to meet it? Well, because the acceleration of the Earth is minute, very, very small, very, very small number because of its inertia. It has a huge inertia compared to this object. That's why this object's accelerating in speed. You can actually measure its acceleration. The other one is so small that you cannot really calculate it. The same principle applies for the cannon and the cannonball in this case, action, reaction. And that's why they have this recoil motion. The only reason why you don't see the cannon itself moves as far as the cannonball moves forward is because of, again, the masses in here. Usually they have huge masses. So what is this one? A bus colliding with a bug. Again, the bug will suffer more consequences because it has more acceleration. As a matter of fact, its acceleration is so big that it can damage it. Whereas the bus, its acceleration is negligible during the collision. Okay? They are both the same force. If two people have the same mass and they push one another on a slippery ground, then in this case, they both should have the same speed in opposite directions. Okay? Now, which comes to the last topic of this chapter, which is the system. You really have to have a specific in here to know what system you're talking about. If in case you have an orange in here, this is your system. Anything outside of that is external to it. So if you have, for example, an apple pulling on it, in this case, the apple is external. So as far as the orange is concerned, that's an external force. So it's going to accelerate, and you can do F equals to ma, which is the second law in this case. If you include the apple inside and it becomes part of the whole system, then those two forces are internal, and the entire system, I'm not talking about an apple or an orange in this case, we're talking about the combination of these two, should not be impacted by this force. In other words, the center of mass, and we're going to talk about that down the road, will not change its location. Yes, the apple can move this way, and the other one can move in the opposite direction, but as far as the center of mass, it should not really move in one way or the other, okay? The entire system, that is. I'm not talking about the one or the other. Of course, you're looking at the ground and you're saying, oh, it's moving. Well, if you include the ground with it, then That's an entire system. If you don't include the ground with it, then you have an external force. That's why that external force is moving your entire system. Okay? So you see the center of mass changing in here because one of them is interacting with the external system, namely the ground. Okay. The force of lift, that's something that is basically, again, when lift equals the weight of the helicopter should hover. Again, we have two forces. One is pulling down, which is its weight, and the lift is trying to lift it. So in this case, you cancel the two, and the helicopter should not go anywhere. When lift is greater, the helicopter should climb in this case, okay? And there is techniques involving the shape and the geometry of the wings, or in this case, the blades of the propeller that should give it the blades should give it a lift so that it rises. That is Bernoulli's law, by the way, and we're going to come to that one down the road. Why planes take off? Okay, a bird flies again because it's going to produce enough lift, pushes the air down so that the air will push it upward. Because of the shape of the wing, the plane actually takes off initially, but then if you switch it a little bit, if you change the angle with which the pilot changes the orientation, then the plane actually will climb in the air. Okay, I think we covered everything in this chapter, and we were able to do an activity. Next time, we'll probably have to modify that activity a little bit to make it a little bit more... Like I said, you will have an assignment for this chapter. This recording will be posted later on for the people who did not make it today. And I know about half the class today actually a little less than half the class did not make it. So they can benefit from it too. And I will see you on Tuesday on the same link on Canvas, basically, when you go to Confer Zoom, so that you see the link there. And we'll meet in the same time as we meet today. And I will communicate with you guys before that. Don't forget you have an assignment that is due this Saturday, the initial reply if you did not do that. Don't forget also to include a picture of yourself, okay? And don't forget to reply to your peers, which is due on September 1st, okay? Please take care and be safe. Thank you.
I have a question.
Yes, go ahead.
Do we have to post anything on the discussion for these?
No, this week you don't have to post anything on the discussions, okay? But next week, yes, okay? Next
Awesome,
week.
thank you.
Yeah, this week because I can basically look at the at Canvas and see who's joined in, who's doing things. It helps me because there are some requirements for the college in terms of students who don't participate and things like that. So I can track this one, that's easy. But next week, there will be specific assignments related to these discussions where you really have to post replies in there, okay? So this week is fine. Thank you, Sarah, for that question. Anybody else?
Yeah, sounds good, thank you.
Okay, see you guys next week.
Have a good weekend. Thank you.
All right, thank you.
Okay, bye.